Hi statisticians, today's lesson is on experimental design. Let's jump in. Some of the most in-demand research positions and jobs are in STEM, science, technology, engineering, and math. Research positions and jobs in these areas tend to come with higher salaries and can be pretty rewarding. However, for a long time, there's been a persistent gender gap in STEM research and in STEM careers. Now, before we explore those gaps, let me name something right off the bat. When analyzing gender gaps in STEM, most of the data collected in the field tends to only capture folks who identify along the gender binary, male and female. There needs to be more data collected on people working in STEM who don't identify by this binary. So even though I'm talking about gaps along the binary lines, there's a more insidious gap here in that we don't have good data that describes truly everyone who researches or works in STEM fields. We need more precise data in the future to address that issue. However, even if the data that we have does not fully capture everyone, it's still worthwhile to analyze these trends among what we can already see based on the data that we already have. And it's pretty clear that males have traditionally been overrepresented in STEM research, with nearly 65% of all science papers authored in 2005 being male, with only 35% being female. And that gap becomes even more extreme as we look at specific STEM subfields such as engineering, physics, and math. Even more recently, as of 2020, workplace surveys have shown that a stark gender gap exists in the relatively newer field of data science. This is something that I, as a statistics teacher, take very seriously, as I teach students along all genders who are amazing in terms of their capabilities and want to pursue statistics and data science in their careers. So, with this type of large gap, I feel very concerned, and I think it merits further investigation for potential causes. And that brings us to our question for today. What causes gender gaps in the STEM fields? With that question in mind, let's move into our notes. We're going to cover 3 topics today, starting with extraneous variables and confounding. So, we're wondering, why are there gaps in the science, technology, and engineering math research field? One theory might be that there is hiring discrimination in STEM research labs. If that's the case, if we were to investigate a bunch of STEM research labs, we might find that the labs discriminate in their hiring practices, and that this discrimination causes the gender gaps we see in STEM research. But there is other possible explanations. It could be that fewer women are applying for STEM research jobs. So the gaps could still occur without any direct discrimination in hiring decisions. Or it could be that many labs receive more qualified applications from male applicants, resulting in the final gap in who they hire. Or it could be that female applicants disproportionately apply to more teaching-focused labs, which tend to focus less on publishing research. So that results in a gap in the authors of papers down the road. Or it could be that female applicants disproportionately apply to Tier 1 university labs, and those labs are more selective in who they hire. So they hire fewer people in general, so fewer females are selected because of that application process. And as we can see, there are in fact many possible causes for the gender gap that we see. So to recap, our initial theory is that hiring discrimination may cause gender gaps in STEM. So hiring discrimination is our explanatory variable, and it's explaining trends we see in the response variable, gender gaps in STEM. But there are other variables that may also influence these gender gaps, and we call these variables extraneous variables. When these extraneous variables are associated with both the explanatory and the response, they are called confounding variables. In other words, they confound the relationship between our explanatory and response variables, making it unclear if they actually have true causal connections. or if they just coincide with the other factors at play. Hence, when confounding is present, we can't draw causal conclusions with these other confounding factors at play. We can't say for certain whether hiring discrimination is the ultimate cause. So, how do we get around all of that? Thankfully, we have a way, and it involves designing good experiments. A group of Yale researchers conducted a now famous Jen and John experiment to try to directly test for hiring discrimination. They made fake job application materials that were completely identical except for one aspect, the name. They made some application materials for a fake applicant named John and others for a fake applicant named Jennifer. Everything else, including all the information on the resumes, personal statements, etc., were completely identical. The study included 127 science faculty from labs all over the country. The researchers then took their fake job application materials and randomly assigned the lab faculty to either receive a John application or a Jennifer application. In total, 63 lab faculty were randomly assigned to evaluate the John application materials, and 64 were assigned to receive the Jennifer application materials. After evaluating the application materials, the faculty then rated the applicants for their competence in hireability, and they also estimated their starting salaries. These evaluations were then compared across the two groups. Before looking at the results, let's look at the components of this experiment. The science faculty members were what we call the experimental units, or the subjects of the study, and they were randomly assigned the treatments. The explanatory variable, the thing that we believe will cause the difference and is the only variable that changed between the treatment groups, is the gender of the name of the application. The treatments applied here is the name John or Jennifer on the application materials. And finally, the measured response variable is the ratings that the faculty gave the applications. To make sure we have a good causal inference for our study, we have to make sure that it satisfies these principles of experimental design. There's 4 of them. First is comparison. The study must compare at least 2 treatment groups. In this case, the study is comparing applicant evaluations across the John group and the Jen group. So we accomplished that principle. Next, there has to be random assignment of treatments. This would be very important, and it's the most important of the 4 aspects. Here's why. Among the 127 science faculty, extraneous variables still potentially exist, as we mentioned earlier. Some of the labs may be teaching focused, some of them may be at Tier 1 universities. By randomly assigning each lab, we can make sure that they get dispersed equally. So we get groups, and the distribution of these extraneous variables should look like this. When we put them all together, we can see that the random assignment balances the extraneous variables between the groups, helping to make sure that both groups got about an even amount of faculty from labs that are more teaching focused and or are more selective. That means that these variables will no longer confound the relationship between gender and hiring, since they are now included evenly in both groups. As we saw in the Jen-John study, they did in fact randomly assign the faculty members to receive either the Jen or John application materials. Hence, the potential for confounding is reduced and the random assignment principle is satisfied. Now, if there's repeating, random assignment is the most important principle of experimental design, and that's because it is the key that unlocks causal inference by allowing us to see causal trends without confounding getting in the way. And another quick note, when we talked about sampling in an earlier lesson, we saw that random sampling reduces bias, and now with experiments, we say that random assignment reduces confounding. These concepts are analogous, and it's important to get the vocab right in the different scenarios. The next principle of experimental design that comes into play is replication. And here's what this means. It means that we should have many experimental units in each treatment group. Imagine for a moment if we only had 2 science faculty in this experiment, and that both of them really like to have coffee in the morning. But in one of the offices, the coffee machine is broken. And that person, you can imagine, is in a bad mood that day. So when we randomly assign one of the faculty members to receive the John application and the other to receive the Jennifer application, it just so happens that the person in the lab with the broken coffee machine gets the Jennifer application materials. And when they go to rate the applicant, it turns out that Jennifer gets a very bad rating. And it's because they happen to be in a bad mood that day. So it's hard to tell if they rated that person badly because they were discriminating against them or because they were in a bad mood because they had no coffee that day. However, if we get more participants in each group, a lot more participants in each group, the effect of the broken coffee pot is minimized. And that's why it's so important to have replication, including many experimental units in each treatment group reduces the impact of a chance variation in the extraneous variable between the groups. And it makes any effect of that treatment easier to detect. We had, in our experiment, 63 people in one group and 64 in the other, so we had adequate replication in the Gen-John study. Our final element is direct control of extraneous variables. In our Gen-John experiment, the applications were identical other than the name at the top of the application. This eliminated the possibility of labs receiving fewer female applications or that the male applications were more qualified. Since all of the science faculty were looking at the same qualifications and exactly half were of each gender, we had direct control over these further variables. Therefore, the Jen and John experiment accounts for all of the components of experimental design. And since it was a well-designed study, that means that causal conclusions are possible. So let's finally look at the results. It turns out that the applicants with the name John at the top received a higher ability score of 3.8, a competence score of 4.1, and an average starting salary estimate of $30,238. And for the Jennifer application, which remember was completely identical other than the name, had a competence score of 3.3, a mean higher ability score of 2.9, and an average starting salary recommendation of $26,508. So we can see that in all of the categories, Jennifer was scored lower than John, even though it was the exact same application. And it turns out that all of these are what we call statistically significant in terms of how much lower they are. Remember that this means that these are differences that are unlikely to occur by chance alone. And we'll study the idea of statistical significance in more depth later on in the course. Just know for now that these differences did not happen by chance alone. They are statistically significant. A final aspect to think about in terms of experiments is the idea of placebos and blinding and what role they play. The control group is a comparison group that does not receive the treatment of interest. Let's look at an example involving scarecrows and how they help or don't help with crops. In this case, we would have a whole bunch of fields growing crops, and about half of those fields would be randomly assigned to receive a scarecrow, and the rest would not receive anything. So we would end up with 2 groups that look something like this. And the group of fields that don't get anything at all are called the control group. Now, sometimes rather than having no treatment at all, the control group gets an inactive treatment instead. Now here's why. Imagine that you give your younger cousin a glass of water and you tell them a small lie, that the water contains a new kind of invisible and tasteless sugar in it. They drink it, and about 20 minutes later, they might be acting like this. This is called the placebo effect. It happens when, even though a participant gets an inactive ingredient, called a placebo, the belief of receiving treatment leads to a measured response. The placebo effect is quite common in medical contexts. For example, placebo pills with no active ingredients have been shown to produce real benefits in examples involving migraines, blood pressure, asthma, arthritis, and other illnesses. This shows the strong connection between the brain and the rest of your body, where sometimes believing in a treatment, even if it's not there, can yield true physical effects. In an experiment, to control for the placebo effect, it is best to give the control group a placebo, such as a sugar pill or a saltwater IV drip. That way, you are controlling for the placebo effect, and both groups believe that they are receiving a treatment. Studies that involve placebos fall into two categories. In a single blind study, either the subjects or the researchers who interact with them are unaware with who is receiving the active treatment and who is receiving the placebo. In a double-blind study, both the subjects and the researchers who interact with them are unaware of who receives the active treatment and the placebo. These setups are sometimes also called single-masked or double-masked studies. So, why would we choose to blind the subjects? Well, blinding the subjects controls for the placebo effect, since everyone thinks they are potentially getting the treatment. But why blind the researchers? Well, blinding the researchers prevents direct confounding when researchers may bias the results. For example, if researchers are trying to prove that a treatment works, they might favor the treatment group in their measurements, thereby unconsciously affecting the results. If they don't know who is getting the treatment and who is in the control group, they won't be able to look at the participants in different ways. So that brings us to our discussion for today. The John and Jen experiment showed that the name caused these differences in how the fake applicants were evaluated. Considering the gaps that exist in STEM, our question is, does the Jen-John study prove that hiring discrimination is the only cause of gender gaps in STEM? Or might there be other causes as well? Explain. Take a moment to jot down your initial thoughts to these questions, and we'll discuss it further in class. That's it for today's statisticians. We'll see you next time.